Right, so hello everyone. My name is Antonio Manesco. I'm a postdoc at the Quantum Thinker Group at the Delft University of Technology. And today I'm gonna present to you our recent work. It's a device proposal where we try to set up the minimal device to perform what we call fermionic quantum computation. So instead of doing quantum computation with qubits, we propose a device that manipulates directly fermionic degrees of freedom. And for that, we use these Cooper pair splitters. So I'll get into that during my talk. But before I start, let me just thank all my collaborators here, and particularly kudos to Kostas, who did a lot of the heavy lifting here. And by the way, if you're looking for a talented postdoc, I'm pretty sure Kostas is now looking for his next academic adventure. So keep that in mind. Yeah, so also, if you have questions anytime, please feel free to interrupt me. I think Kostas is also keeping an eye in the chat, so he'll also interrupt me if you write something in there. So yeah, let's get started. First of all, let me make a disclaimer here. I'm not an expert in quantum computation. My expertise is in mesoscopic physics and condensed matter. So this is not really a talk about quantum computation, but rather about a device. But in any case, at some point, I had to learn one or two things about quantum computation during this project. And, you know, I just did the same thing that everyone does. I just went to Google and tried to understand why we would like to have a quantum computer. And if we do that, we actually find a few nice ideas out there. For example, things ranging from machine learning to financial modeling, cybersecurity. Well, the list goes on and on and on. But you know, if we are actually more familiar with the field, we know we're not quite there yet. We still need some time to actually be able to apply quantum computers to all these contexts. But rather what we see in the literature, the more like state-of-the-art applications of quantum computers are on cases that are more like these ones. So this is a work from the Google collaboration where they realize topological order states with the quantum processors. Meaning that what they're mostly trying to do here is actually try to understand phases of matter with the quantum computer. And this is actually somewhat the idea that, well, even if we go back to the early ideas of quantum computer by Richard Feynman, for example, this is pretty much the main application of quantum computers that we ever had. So if we now try to think about how to actually solve these specific class of problems, we start learning a few things. So we know that then that quantum computers are good for solving quantum problems. So if we have an actual quantum system that we want to understand its dynamics, ground state, excited states, this is where quantum computers are probably very good to solve these problems, and we don't really need to understand the scaling of the problems or whether there is some actual advantage or not. Because here the quantum is actually built in. So let's try to find one quantum problem. And we could start by thinking about, for example, quantum chemistry problem, where we have a bunch of electrons that interact in an environment. So now if we get this quantum chemistry problem and try to translate that into a quantum computer, we need to perform a few steps. And the very first step that we need to perform is actually because quantum computers, the standard ones, operate with these qubits. And these qubits have a very particular algebra, so they follow this Pauli algebra. And whereas quantum chemistry problems, where we were trying to deal with the dynamics of electrons, we actually have fermions, and fermions have a very different algebra. So because those two don't correspond exactly to each other, If we're trying to simulate fermions on a quantum computer, we actually need to somehow translate this fermionic algebra to our qubits. And we do that, well, for example, using this Jordan-Wigner transformation. There are other ways to do so, but just to give you an example on how you try to tackle that. And one thing you can notice from this transformation is that it's, first of all, fairly non-local. So we have these tensor products here with a bunch of terms. And well, you will always have to perform that anyway if you want to do a simulation of a fermionic system. So because this transformation is highly non-local, the resulting Hamiltonian is also going to be non-local. And second, this transformation itself adds an extra overhead to your quantum computer. So every time you want to run a simulation of a fermionic system, you need to go through this transformation, and then you have a built-in overhead for any problem that you try to solve. So what if we just forget about a qubit quantum computer and we try to directly control fermionic degrees of freedom with our quantum computer? For that, we need a few things if we are trying to actually tackle these questions. First of all, we need a recipe on how to actually do this control, this universal control. And second, we need a device. So for the first part, the recipe, this has been worked out actually more than 20 years ago by Kitaev and Bravyi in this paper right here, where they show that if you have a fermionic system and you want to do universal quantum computation with this fermionic system, you actually need to be able to implement these 4 gate operations. So, and let me just make a remark here. Now we're not necessarily talking about a quantum simulator anymore, but we're actually trying to build a universal quantum computer, so the same way as you would do with qubits, but with fermionic degrees of freedom. So let's try to understand a bit the physics that we need to actually control if we want to implement all these gate operations. So first of all, we have all these exponential here that we can think as some time evolution of a Hamiltonian. And the first one is pretty much changing the energies of some states. The second term is causing like transitions between one state to the other. The third one is a bit tricky because we need to create now pairs of fermions in different states. And finally, this fourth term is an interaction between fermions that are in different with different quantum numbers. So how do we actually, if we were willing to implement all those gate operations, how would we actually do? And for that, we actually need to start thinking about a device. So I'm doing mesoscopic physics, and the very straightforward way that I think to actually try to isolate a fermion and manipulate its degrees of freedom would be to start confining one fermion in a quantum dot. Right. So if we think about a device, I'll try to move from now on with a device that is based on quantum dots. And there are many ways we could actually confine. So here I illustrate 2 ways, which is already showing a bit the next steps of my talk. So we could have, for example, electrons confined in a one-dimensional channel to start with. So for example, a nanowire, which is what you see in this left figure. And now, well, electrons can still move freely in this one-dimensional channel, but now if we actually apply a bunch of gate voltages to confine these electrons, we can actually confine them into a zero-dimensional region, which is what in this figure is shown by the dashed lines right here. So we could create these quantum dots in a nanowire, or we could instead imagine taking a 2-dimensional electron gas and creating actually a gate pattern now that also confines the electron in both directions, which is done here in this right figure by the gates that are shown in colors red and blue here. So the red color creates a one-dimensional channel, this gray channel here in the middle, and the blue gate voltages confine the electrons in a zero-dimensional region. So okay, this is the starting point, but let's also try to build a few conditions that we want for the operation of these devices. So we'll try to keep in every single quantum dot a single fermion at most. Meaning that, first of all, we want one electron, at most one electron per dot, meaning that we want a very large charging energy, such that the cost to add a second electron to this quantum dot will be very, very large. The second thing in the target regime that we have is that all fermions have well-defined quantum numbers, and this is important for us to understand better how to control their dynamics. So we do that by applying a large, imagine that we apply a large Zeeman field that polarize the spins of these electrons. So we could think then that the most minimal device, which would be analogous to a 2-qubit system, would be a set of 2 quantum dots where we can control their degrees of freedom. So here I'm illustrating 2 quantum dots that are spin polarized, and you can construct these quantum dots by confining them with gate voltages. So this already gives us pretty much for free control of the on-site energies of these dots, because now if we have a plunger gate close to this quantum dot here, we can actually control the chemical potential of this quantum dot, and by just ramping up and down this on-site this chemical potential, we actually control directly this first gate operation. Now, almost for free as well, we get the second gate operation, which is pretty much a hopping between those 2 dots. So if we allow electrons to hop from one dot to the other, we already get the second gate operation. And we could do that by having a gate voltage here in the middle where we can control and set the tunneling probability for electrons to go from the left to the right. And as they do that, as we control this process, we also already implement the second gate operation. So, okay, now we have 2 out of 4, which is not bad, but there's still 2 gate operations left, and those are the trickiest ones. Of course, that's why I started with the other 2. So the third gate operation that I showed you was this one, where we're creating pairs of electrons with different quantum numbers. So it's a creation and annihilation, a coherent creation and annihilation of pairs of electrons. And how do we even do that, right? And this is where the Cooper pair splitters come in. So the idea goes like this. We now have these 2 quantum dots, and we place a superconducting region in the middle. And now in a superconductor, we have this condensate of Cooper pairs. And we can think of a process where a Cooper pair comes from the superconductor and splits such that one electron goes to one dot and the other electron goes to the other dot. This is the process that that is sketched here by this acronym CAR, which stands for crossed underarray reflection. But also there is another process that could happen in here, which is called elastic cotunneling, which is pretty much just the tunneling from one dot to the other. So those 2 processes are definitely possible. And if we have now a device that looks more like this, we could already implement 3 out of the 4 gate operations. But we still need to figure out how to control actually the rates of those processes. And in fact, those devices are very similar to what our colleagues here in Delft are doing. Also, a bunch of other people when they try to build these Cooper pair splitters. But we are heavily inspired by their work because, well, they have pretty much what all the ingredients that we need. They have two quantum dots here, which are shown by these wells here. In the middle, they have a superconductor, and the superconductor is actually proximatizing the nanowire. So it's not like just a block of superconductor in the middle of the wire, but is actually proximatizing the semiconductor that is forming this quantum dot. And there they can actually control the rates between this cross-dendrive reflection and elastic cotunneling. So that inspired us to use as a starting point for our device. To show how that works, so let me go through these two panels here. Here I'm showing two possible configurations for quantum dots. You could imagine that you have quantum dots that have anti-parallel spin configurations or parallel spin configurations. It doesn't really matter. Both of them work pretty much the same way. So what I'm showing with those colored lines, the orange line is the probability of cross-dendrive reflection. So this idea of an electron coming from the superconductor and splitting into the two quantum dots. And the blue line is the elastic cotunneling. So this tunneling process via the superconductor to the other quantum dot. So now you see that the x-axis here is actually the chemical potential of the region in the middle. So that region that was coated by a superconductor was actually a semiconductor proximatized, and by controlling the chemical potential of that middle region, we can actually tune these two processes, the cross-dendrive reflection and the elastic cotunneling, such that we, for example, could park at when this chemical potential is equals to 0. So let's look at this more faded blue line here where it goes exactly to 0. We have no elastic cotunneling, but we have cross-dendrive reflection, which allows, for example, to have the third gate operation that I showed you without any others. But you see here that also there is a small caveat here. These two processes always come together in some sense. So the blue line, in every point, the blue line is non-zero. The orange line is also non-zero. These will pose a small problem that I will comment on a bit. But you see that in both spin configurations, it works pretty much the same way. And yeah. By the way, if you have any questions at this point, would be actually a great point to have a small pause. So do raise your hand if you have any questions. Okay, I don't see any questions, so I'll move on. All right, so we now take these poor Uranus device, which are how our colleagues kind of these devices where they have this Cooper pair splitter connected to two quantum dots. And that's mostly because they're trying to understand this Majorana physics, which, by the way, is kind of already an application of the device that we're proposing, because here you can coherently control all these processes such that you could use as a simulator of a Kitaev chain. But we want to do more. We want to do universal quantum computation. So let's try to add the remaining gate operation that we need to get a universal set of operations, which is an interaction term between the two quantum dots. So this is how we envisioned the device. Well, at least the first version of it. And you see that we have pretty much the same ingredients that I just mentioned to you. We have a superconductor proximatizing an island here in the middle, and this island is actually coupled to two quantum dots via two types of process, just a regular tunneling and a tunneling that depends on the spin-arm coupling that also allows for spin flipping. And besides that, we also connect here a tunable capacitor. And this tunable capacitor will implement this last gate operation that controls the interactions between the states, the fermions in the two quantum dots. So, all right, this is the basic device. So let's look into that with more detail. So as an example, let me just show you that we can, for example, implement time-dependent gate operations with it. And I will exemplify that with a gate operation that takes electrons that start in the, let me see, they start unpopulated. And as we tune it in, we actually create a pair of electrons, one at each of those dots. And this is the process that causes this is the process this cross-dendritic reflection. So we take a Cooper pair from the superconductor and split into those two dots. We can control the rate of this process by just controlling tonal barriers. And here we show how the different ramps for this gate will actually work. So you see that pretty much all of them do the job, except that if we make these curves smooth enough, we actually don't, when we go to the left panel, we don't see these wigglings, meaning that we actually don't have any extra processes happening. So this is mostly showing that we need to perform the process adiabatically if we want to make sure that the gate operations work fine. And the wiggly lines here are actually just because if we ramp up these too fast, we end up populating the states in this middle superconducting island. So you see in this panel C here, the population in this middle island, and you see that if we try to make it the gate pulse as adiabatic as possible, we keep the population minimal. So, all right, we managed to implement some gate operations, but again, there is a few of them that are a bit tricky. So, and the one that is trickier, I would say, is this elastic cotunneling process, where an electron go from one dot to the other. And the reason why this is tricky is because every time you try to turn on this process, you actually also renormalize the on-site energies of the two quantum dots. And this normalization in the on-site energy actually gives you an operation that is not really orthogonal to the on-site operation in these two quantum dots. So this horizontal arrow here is just showing what would be a pure hopping, and the vertical arrow is showing what is the control of the on-site or the chemical potential in those two dots. And when we turn on this elastic cotunneling process, what we get is actually something in between. So there are ways to solve that. So we need to reorthogonalize these operations, but it requires many steps. So we work that out, but you see that there is like this product of many operations that we need to kind of purify the gates. That depends on how much non-orthogonal they are. So if they are very close to be completely parallel, then you need to do an infinite amount of operations to orthogonalize, but luckily they're usually not that bad, and with 5 or 6 operations you can actually reorthogonalize those gates, at least based on the experimental numbers that we got. All right, well, there is a way, but perhaps it's not ideal. So at this point, we realized that our device works. We managed to implement all the gate operations that we needed. We have a recipe for them. But we started thinking, is this device really good after all? Can we, should we actually recommend people to use this device, or can we actually do better? And there are a few problems that we spotted on the way. So first of all, we were talking about quantum dots, and we control pretty much everything in the Hamiltonian with those gate voltages, which makes this device highly sensitive to charge noise. So every fluctuation in the voltage could actually cause something in the Hamiltonian. To be more specific, the estimated coherence times of these devices is about 1 nanosecond, and the lowest theoretical bound for the gate pulses that we could possibly get, even if you have very fast electronics, is 50 picoseconds, which gives you about 20 gate operations before you lose coherence, which is doesn't seem like the optimal quantum computer that we would like. And another problem is that we cannot really just turn off superconductivity, and this is related to the last slide that I just showed you, because we now have just a single parameter to control cross-the-drawer reflection and elastic cotunneling. And because of that, we actually get these non-orthogonal gate operations that we need to fix. So if we somehow manage to fix those two problems, we believe that device would actually work much better than our original proposal. And this is how I want to spend the remaining time that I have to give you the solution for all these issues with the second device. And maybe you actually think that this device looks exactly the same as the last one that I showed you. The differences are not that big, which actually makes it quite interesting because, well, so the main difference here is that we're now connecting these two altered quantum dots also to the superconductor. And moreover, we also have those tunneling probabilities from the superconductor to each dot, and we assume they are tunable. So these now could not work anymore in a nanowire device. We probably rely on two-dimensional electron gases to work. But if we can now tune independently those couplings and connect all those dots to the superconductor, we actually solve the two problems that I just listed at once. First of all, we can turn on and off superconductivity by controlling these the tunneling barrier between the superconductor and these quantum dots. So this already gives us a set of orthogonal gate operations, because now we could actually have a process where we have purely elastic tunneling or cross-the-drawer reflection without the need of re-orthogonalizing everything. And the second part is perhaps a bit more subtle. It's possible also by tuning the chemical potential of these dots once they are in proximity to a superconductor, to a sweet spot where these dots are actually charge neutral. And because they are charge neutral, all the sensitivity to back gates actually becomes quadratic, which actually help us quite a bit in these coherence times that I just showed. So by just doing this very small tweak in our device, we actually fix both the orthogonality of the gate operations, and we also fix the sensitivity to charge noise. So how do we see now moving on from this device? Well, of course, it would be great to have more fermions. So perhaps we could imagine stacking those dots in a chain, for example. Perhaps we can also get rid of these external capacitors. So this is an idea that we discuss in the manuscript. You see that this superconductor now is grounded. Maybe by changing between grounded and floating, we could actually tune the capacitance between these dots and get these gate operations kind of for free without the need of an external capacitor. And also would be great to have an experimental group willing to fabricate a measure. We'll be happy to help if you are interested. And yeah, with that, I would like to end my talk. So just to summarize, we proposed a building block for a Fermionic quantum computer. This is pretty much analogous to a 2-qubit, a universal set of 2-qubit gates. There are similar devices out there, for example, this Wimmer device, except that now we would need to add this capacitive coupling between these two quantum dots. We also show a recipe on how to implement all those gate operations. And finally, we show that tunable couplings to a superconductor of all those dots to a superconductor would actually both suppress charge noise and simplify the gate operations. So with that, I want to thank you